This is a short screencast looking at C charts and X bar charts in particular. Try to keep these under 10 minutes if I can. And I wanted to take just a few minutes to look at C charts and X bar charts, as I had mentioned. We'll start off with X bar charts. And of course, go into QM for Windows. Load that up as we've done multiple times. Then actually go to New. Click on, you've got a choice between P charts, X bar charts, and C charts, and you would click on C charts. For this data set, it's the creation of a quality control system looking at the manufacture of paper airplanes. And so I've created what you can see is the data here. Just simply click on raw data, put in the number of samples. And for us, the number of samples is 5. We've got 5 workers, and then our sample size, so it'd be 5 workers, and our sample size here is 4, so 4 samples each. Now, if I clicked OK, it would create the template. I've already filled it out here, so I'm going to just click Cancel and look at our situation here. This is actually fictitious data looking at the length of the fuselage of a paper airplane. And for instance, 12 inches to 14 inches, you can see the range here on our first one is, the low of 12 and the high of 14. So our range is 2 for worker 1, so on and so forth the whole way through. QM for Windows will do all these calculations for us easily. And so what I'll do is simply go to Solve. Oh, incidentally, you can choose whatever you want as far as the quality control chart level of significance. I've chosen 3 sigma or 99.7% for the level of significance. Click on Solve, and you can see that it runs all the data for you. First of all, for worker 1, incidentally, I plugged in, it says sample 1, plug in worker 1. It allows you to keep your ideas fluid and organized. But for instance, for worker 1, their average or center line mean for that one worker is 12.65. For worker 2, it's 12.17, so on and so forth. It adds these together, divides by 5, and it gives you your grand mean, or your overall average of 12.53. Same thing for the range here. The high versus the low. You'll recall we were looking again at worker 1. The difference between 12 and 14 is 2. When we solve this off, you can see that they've done all that mathematics for you. The biggest range is worker 2. However, they add all these together, divide by 5, and they get the center line of 1.04. I'm going to go back to our data one last time and look, for instance, worker 1, the average can be as high as 14, but look at worker 5, 14.2, 13.7, 14 seems to be an outlier. And we'll see if this appears on our control chart. Incidentally, QM for Windows runs our control chart, our X bar chart, as well as our range chart. So our upper control limit, lower control limit, and center line is right there for our range chart. For our mean chart, our upper control limit, center line, and lower control limit is right there, making it really convenient. Simply click on Window, go to Control Chart, and it will run that control chart for you. Let me bring this down a tiny bit so you can see. We've got our samples right here, our 5 workers. We've got our control chart with our upper control limit of 3.28, center line of 12.53, and our lower control limit of 11.77. We actually can also click on and get our range chart, and our range chart is right here. Again, our upper control limit, center line, and lower control limit. So we can run those real quick and easy, going back and forth, getting a sense of our data, whether it's from the results and doing all our calculations here to our full control chart right there. One last thing I'm going to do, actually I'm going to click out of this real quickly and dump that. It's my sailboat. And let me get C charts. And again, I pulled this data together for your convenience, and also to make this a little quicker. But as we can see, this is the number of defects on a paper airplane. And for instance, it may be a wrinkled wing, it could be a spot, it could be the way it's folded is incorrect. Anything that you decide as a key success factor, if there's a defect in that key success factor, you'll want to put it in. I've taken actually 20 samples. It's our 5 workers times 4 samples each, and I've loaded all that in from 1 defect from our sample 1 plane, 6 defects in number 2. Actually 6 seems to be our highest number of defects. And the beauty is you arrange this again, File, New, go down to C chart, click on C chart, and then the number of samples here would be 20, so you would click that to 20 and click OK. I'm going to cancel it so I don't have to reload the data. But all we have to do now, after getting all the data in regarding our defects in paper planes, click Solve, and I've got our total number of defects, the total number of samples, our defect rate, which is our center line, and you'll see that in a second, and also it runs our standard deviation for you for whatever value that might be. It also runs our upper control limit, and you'll recall we have the equation for C charts as the upper control limit is equal to our center line, our C, average number of defects, minus our sigma. And we're going to do this again at 99.73 or 3 sigma times the square root of our center line or our average. And you can do this by hand, or you've got the upper and lower control limit right here. Also remember that your lower control limit, actually in this situation, I hand calculated, it's a negative 2.15. We have to use a 0, however, because you can't have less than 0 defects. So even though the mathematics doesn't have a non-negativity component, actually here it does. It'll put 0 in for you. But if you actually ran these numbers by hand, you would find that you would have a negative lower control limit. It just resets it to 0. Having described our upper control limit, our center line, and our lower control limit, I simply click on Solve, and I can bring up our control chart for this C chart. And you can see with our upper control limit of 8.7 defects and our lower control limit of 0, we actually have, and our center line of 3.3, we have a system that's in relative control. Lastly, having said that, this is the mathematics we use to set our initial control chart. We may decide that we cannot endure more than 2.8 defects. As a result, we would have to recalculate or recalibrate our system in order to begin to shrink that down, the number of defects, identify our kind of problem children and issues that may be leading to the higher defects, all those frankly up above the center line, and begin to rerun production so we can avoid this number of defects and the amount of scrap that we're producing. Thank you very much for listening to this presentation. I hope it was of value. Take care.